tend to think of time as something steady and predictable, always ticking forward in the same way. You check your watch and a minute feels like a minute. But what if I told you that time doesn't always flow the same for everyone? In fact, time can bend, stretch, and even slow down depending on where you are. Imagine you and your friend are on a futuristic space adventure, flying in a spaceship close to the speed of light. At first, everything seems normal. You're both communicating, seeing each other, and time feels the same. But as your friend's spaceship starts accelerating faster and faster, getting closer to light speed, something strange happens. From your perspective, it looks like your friend is moving slower and slower. Their ship seems to crawl through space, and every movement they make seems to take ages. Even their messages start arriving more slowly, as if someone is stretching them out in time. It's like watching an old video in extreme slow motion, where everything drags on longer than it should. But from your friend's point of view, inside the ship, nothing is weird. To them, everything is normal. Time passes at the usual pace. Their ship is moving just fine, and they don't notice anything unusual about their own movement. It's as if they're still on a calm, regular journey. So why does this happen? What is it about speed, massive objects like black holes, that make time slow down for someone nearby? And if time can behave so differently in different places, is it really as constant as we thought? It all started with an apple. Legend has it, one day in the 1600s, Isaac Newton was sitting under a tree when an apple fell to the ground. That got him thinking, why did the apple fall straight down? What force was pulling it toward the ground? Newton's big breakthrough was the idea of gravity, a force pulling objects toward one another. But his thinking didn't stop there. Newton believed that time, just like gravity, was the same for everyone, everywhere. He thought of time as absolute, ticking forward at a steady rate, no matter where you were in the universe. In his view, time moved at the same pace for someone standing on Earth as it did for a person floating in space. For centuries, this idea of absolute time worked. It made sense for most situations in everyday life, but Newton still couldn't explain how objects like the Earth and the Moon could influence each other from a distance. And he couldn't have guessed that time itself might not be so simple. Then, about 200 years later, Albert Einstein came along and flipped everything on its head. Einstein realized that time wasn't absolute after all. In fact, time could slow down or speed up, depending on how fast you were moving or how strong the pull of gravity was where you were stood. Near something as massive as a black hole, time would slow down so much that it would seem almost frozen compared to time on Earth. Einstein's theory, known as general relativity, explained that gravity doesn't just affect objects, it bends space and time. So, instead of time ticking away the same for everyone, it can stretch or shrink based on where you are and how fast you're moving. For example, the closer you are to something with strong gravity, like a planet or a black hole, the slower time moves for you compared to someone farther away. So while Newton's idea of absolute time worked for a long time, Einstein showed us that time isn't a constant. It's flexible, influenced by gravity and motion, and behaves differently depending on where you are in the universe. As we know, right after the Big Bang, the universe was a very different place. It was hot, dense, and rapidly expanding. In those early moments, time didn't behave like it does today. It ran slower, not because something was wrong with our clocks, but because the very conditions of the early universe, its extreme density and gravity, meant that time was stretched. According to Einstein's general theory of relativity, time isn't a constant, unchanging force. It can be warped by two main factors: gravity and motion. In the early universe, the dominant factor slowing down time was gravity. Think about it. When the universe was just born, everything was packed together into a small, hot, dense space. The gravity in this tightly packed space was unimaginably strong. Einstein's equation for gravitational time dilation gives us a glimpse of what was happening. In this equation, T0 is the proper time, the time close to the massive object. Tf is the coordinate time, the time far away from the object. G is the gravitational constant. M is the mass of the object, or in the case of the early universe, the mass-energy density. R is the distance from the object, how close you are to it, and c is the speed of light. What this equation tells us is that, in the presence of extreme mass and energy, like in the early universe, time slows down dramatically compared to how it flows now in our much less dense and cooler universe. The closer you are to massive objects, the more time gets stretched out, and in the first moments after the Big Bang, the entire universe was a massive object. But time dilation isn't unique to the early universe. We experience it even today, under certain conditions. There are two main forms of time dilation: gravitational time dilation and time dilation due to motion. Even now, time runs slower in stronger gravitational fields. For example, time runs more slowly at the surface of the Earth than it does high up in space, far from our planet's gravitational pull. This is the same principle that slowed down time in the early universe. It's just less noticeable on Earth because our planet's gravity is much weaker than the gravity of the entire universe packed into a tiny space. But we can still measure the effect. Satellites in orbit, for instance, experience time slightly faster than we do on Earth, which is why corrections need to be made to GPS systems to account for the difference. We can use the same equation we applied to the early universe to calculate gravitational time dilation for objects like the Earth or a black hole. If you were to approach a black hole, for example, you'd experience time even more slowly than someone standing on Earth. In fact, as you get closer to the event horizon of a black hole, time would appear to almost stop entirely. This is why we often say that nothing escapes a black hole, not even light. The second type of time dilation occurs when you're moving at very high speeds. This effect is described by Einstein's theory of special relativity. The faster you move, the slower time passes for you relative to someone standing still. This effect becomes more noticeable as you approach the speed of light. This is the equation of time dilation due to motion. In this equation, delta t apostrophe is the time experienced by the moving object. Delta t is the time experienced by someone standing still. V is the velocity of the moving object, and c is the speed of light. This equation shows that as your velocity, v, approaches the speed of light, the denominator gets smaller, and delta t apostrophe, the time you experience, also gets smaller. In other words, the faster you move, the more time slows down for you. If an object could somehow travel at the speed of light, time would appear to stop entirely from your perspective. So, how does all of this relate to the early universe? Right after the Big Bang, the universe was rapidly expanding, and as it expanded, gravity began to weaken. This weakening of gravity caused time to speed up compared to how it was in the denser earlier moments. As the universe expanded, the matter and energy that had been packed tightly together spread out, and time began to flow more quickly. But the effects of time dilation are still visible today. When we look at distant galaxies, we're seeing them as they were billions of years ago, closer to the time of the Big Bang. The light we observe from these galaxies has been traveling through space for so long that it has been stretched by the expanse of the universe, a phenomenon known as redshift. This redshift isn't just a stretching of light, it's also a stretching of time. The further back in time we look, the more stretched out the signals become, showing us that time was moving differently in the early universe. In fact, observations of distant quasars have shown us that cosmic objects from the early universe appear to tick more slowly than similar objects today. This isn't because those objects were inherently different, but because the expanding universe stretches everything, including time. This means that the time it took for the light to reach us was longer than it would have been if the universe were not expanding. To make this concept clearer, imagine a graph where the x-axis represents a distance from a massive object, like a black hole or the early universe, and the y-axis represents the flow of time. As you move closer to the object, the line on the graph starts to dip downward, showing how time slows down. This dip becomes steeper the closer you get, representing the extreme time dilation near the event horizon of a black hole or in the early moments of the universe. Time dilation isn't just some abstract concept. It's a real effect that we can measure and observe. It's played a huge role in the early universe, when time ran slower due to the intense gravity and dense energy of the cosmos. And even today, time dilation shapes how we understand the universe, whether it's the time differences we measure between satellites and the surface of the Earth, or the slowed-down ticking of distant cosmic objects. So, while time might feel like it flows the same for everyone, the truth is that time is flexible, shaped by the forces of gravity and motion. And when we look back at the early universe, we're not just seeing the distant past, we're seeing how time itself has changed. Time is not as straightforward as we might imagine. Under certain conditions, it behaves in ways that challenge our everyday experiences. One of the most fascinating examples of this is the twin paradox, a thought experiment that shows how time can diverge based on speed. Picture this scenario. Two twins born at the same time live their lives normally until one of them embarks on a journey through space at a tremendous speed, while the other remains on Earth. For the twin on Earth, life continues as usual. Days turn into weeks, months, and years. But for the twin speeding through space, time passes differently. What feels like just a short trip for them stretches into decades for the twin who stayed behind. When the space-traveling twin returns, they find that their sibling has aged significantly while they themselves are barely aged at all. This isn't an illusion or a quirk of perspective, it's a real physical effect. The paradox here lies in the twins' drastically different experiences of time, despite being born at the same moment. But the twin paradox is just the beginning. As we explore the nature of time, especially when extreme speeds or strong gravitational fields come into play, we encounter other strange and thought-provoking paradoxes that challenge how we think about time and space. One such paradox is the grandfather paradox. Imagine you have the ability to travel back in time. You go back far enough to meet your grandfather before your parents were even born, and for some reason, you prevent him from meeting your grandmother. The paradox is simple. If your grandfather never meets your grandmother, you would never be born. But if you were never born, how could you have traveled back in time to prevent their meeting in the first place? It's a loop that seems impossible to escape, suggesting that time travel could create contradictions in reality itself. Physicists and philosophers have long debated whether the universe would allow such a paradox to happen. Some believe that the laws of physics would prevent these kinds of contradictions by making time travel impossible in the first place, while others suggest that the universe might correct itself, ensuring events unfold in a way that avoids these paradoxes. Another time-related conundrum is the bootstrap paradox. This occurs when an object or piece of information exists without ever being created. For example, suppose you go back in time and hand Shakespeare a copy of his own works. Shakespeare publishes those plays, and centuries later, you grow up reading them and decide to travel back in time to give him the manuscript. But here's the paradox. Who actually wrote the plays? If they've always existed in this loop, then they have no real origin. This paradox, like the grandfather paradox, raises deep questions about causality and the very nature of time. In some interpretations, the universe could allow such a loop to exist, where certain events or objects simply have no clear starting point. The predestination paradox is another intriguing concept. In this scenario, time travel creates a closed loop, where the events are predetermined by the very act of time travel. Imagine you're sent back in time to stop a disaster, only to find that your actions were the cause of the disaster in the first place. No matter what you do, the event you're trying to prevent has always happened, and you're simply playing your part in a cycle that can't be changed. The paradox ties into the question of free will versus determinism. If our actions are part of a closed loop in time, do we really have any choice, or is everything we do already written into the fabric of the universe? As strange as these paradoxes sound, they're not just flights of fancy. They're grounded in the real science of time and space. Einstein's theory of relativity, which brought us the concept of time dilation, also suggests that time travel might not be entirely possible, at least in theory. Time travel into the future is something we already know is possible. Astronauts in space moving at high speeds and experiencing weaker gravitational forces come back to Earth having aged ever so slightly less than the people who stayed behind. This is a tiny example of traveling into the future made possible by time dilation. Traveling into the past, however, is where things get tricky. The paradoxes we've discussed, like the grandfather and bootstrap paradoxes, suggest that traveling backward in time could lead to contradictions that challenge the very nature of reality. Some scientists propose solutions like parallel universes or alternate timelines, where traveling back in time creates a new branch of reality, allowing both the past and future to coexist without contradiction. While time travel may remain a distant dream, the paradoxes associated with it give us a glimpse into the strange and complex nature of time itself. Whether it's the twin paradox showing us how time stretches and bends based on speed, or the grandfather paradox revealing the potential contradictions of traveling back in time, each of these scenarios forces us to question what we think we know about reality. One way to visualize these paradoxes is through graphs or timelines. For instance, in the case of the twin paradox, we could imagine two lines on a graph, one representing the passage of time for the twin on Earth and another for the twin traveling at near light speed. As the graph progresses, the Earth-bound twin's line moves steadily upward, while the space-traveling twin's line starts to curve, slowing down and stretching out. When they meet again, the gap between the two lines represents the difference in the time they've experienced, a visual representation of time dilation in action. In time travel scenarios, a similar graph might show multiple branching timelines or closed loops, illustrating how actions in the past could create alternate futures or lock events into a never-ending cycle. Whether or not time travel is possible, the paradoxes that arise from it help us understand the flexibility and complexity of time itself. The twin paradox shows us that time is not absolute, but rather it bends to the will of motion and gravity. The grandfather and bootstrap paradoxes challenge our understanding of causality and free will, raising questions about whether events in the past can ever truly be changed, or if we're bound to follow a predetermined path. In the end, these paradoxes don't just make us rethink time, they make us rethink everything we know about the universe and our place within it. You are standing on the edge of time, where every discovery about the universe challenges what we think we know. Time, it turns out, is not a constant universal experience. From the early universe to the present day, it has stretched, slowed, and warped, shaped by gravity, motion, and the expanding cosmos. We've seen how, right after the Big Bang, the universe was a dense, hot place, where gravity was so strong that time itself flowed much more slowly. Objects like distant quasars allow us to peer back billions of years and witness a time when everything moved more sluggishly. The signals we receive from these ancient objects are not just delayed because of distance, but also because time itself was stretched in those early moments. This phenomenon, cosmological time dilation, shows that the deeper we look into the universe's past, the more drawn out and slowed down events appear to us. But time dilation isn't just a relic of the early universe. Even today it shapes the experiences of astronauts, satellites, and objects near extreme gravitational fields like black holes. The twin paradox showed us how speed alone can bend time, with one twin aging more slowly simply by traveling near the speed of light. We also touched on the strange puzzles that time travel introduces, whether it's the grandfather paradox, where changing past events could prevent your own existence, or the bootstrap paradox, where something has no clear origin, existing in an endless loop without a beginning. These paradoxes make us question whether time travel into the past could ever be possible without breaking the fabric of reality. In the end, time itself may be the ultimate mystery, one that stretches across the entire universe, from its birth to its eventual fate, reminding us that while we live in the present, the true nature of time is far more complex than it appears. Thank you for watching this video and for joining us on this journey through the mysteries of time. Whether it's the early universe, the bending of time through speed and gravity, or the strange paradoxes that come with time travel, we've only scratched the surface of what's possible. If you enjoyed this exploration, don't forget to subscribe and leave your thoughts in the comments. Also, check out this video on your screen to see how scientists created a black hole in a lab. And I'll see you there.